So in your project, when you model the inductor, there are several options. First of all, right, an ideal inductor is like this. An ideal inductor is just simply this, and then you have L1. Its Q is going to be infinity, right? The quality factor. This is an ideal inductor, right? If your current DC current pass through it, there's no potential drop. That's the first one. And the second one is that you can model it with a series resistor. So it will be like this. RSL1. Make sense? Because the inductor is not a superconductor. It has resistant potential drop, right? The quality factor equals to, not Q1, just Q, equals to WL1 divided by RS. That's how I memorize this equation. It has two components. One is the impedance due to the inductor, omega L1. Another is impedance due to RS. And for ideal one, it means what? Very small RS, right? So it must be omega L divided by RS. That's how I memorize it, right? So your RS is 0, then you have infinite quality factor. Right? You can read the textbook to see how they are derived, or just take it for granted, right? We don't test you for this. But you should know this when people ask you the quality factor, right? You can also model it as with a parallel inductor, parallel resistor. So that is how it looks like. Then I have L1 RP. The quality factor this time becomes RP divided by omega L1, which is also easy to memorize. You want to have an infinite parallel resistor, right? Because if it is too small, then you got short. You don't have the inductance. The effect is gone, right? So I will think RP is at the top. That's how I memorize it, right? So these are three possible way to model that. Now, however, to make it accurate over a band, a wide band, right? You actually want to use the fourth method. And I do not know why I have 1/2 here. Okay, because this is a typo in the textbook. This should be 1/2. Okay, so for this model is that I recognize that it has the series resistance. It also can have this parallel leakage to really model it well. So you see that we have a S, we also have RS and RP. Okay? Now if you plot the Q factor as a function of omega, then you see that it changes as you changes the RP and RS. Again, we do not want to go to the details, but this is a wider band model. Wider band means it is valid for more frequency. So this one is only valid for a very low range, narrow range of frequency. Right? This is a wider band model. The Q maximum of this model is at omega equal to square root RP RS divided by Li, and then the value is equal to 1/2 square root RP divided by RS. And that's why I say there's a typo in the textbook. Basically, this is what is said, right? When your I think there's no square root at the bottom. Do I have? Yeah. Should be only on the numerator, right? So when your frequency is at this, then you will have this Q. So you try to adjust it, right? I gave you the Q, and then you try to adjust the R, P, and L so that you get the right frequency for your operation. And